estimate of the weight of the orange. Will my new estimate be more reliable than the previous estimate?
Yes.
Why?
Law of large number.
No, let's talk logic. Yeah. Will my estimate be more reliable than the previous one? More information. More information. It's based on 2 bits of information. So its reliability will be twice that of one.
Yeah.
Well, that based on one. Or its variance must be half the variance of the guess based on one observation. So if the guess based on one observation is a variance sigma square, the guess based on 2 observations will have sigma square upon 2. If the guess is based on 3 observations, I have sigma square by 3. If the guess is based on n observations, I have sigma square upon n. Right? Sure? As long as, of course, the oranges are independent of each other. If they are correlated, then there is a problem. Right? If somebody has conned me, so all the fatter, thicker oranges are on the top and all the thinner oranges at the bottom, I am only picking up ones from the top, then the chance that I pick up a heavy weighted orange right now, right? If I picked up a heavy weighted orange previously is high, so orange weights are positively correlated, my samples are positively correlated, then the variance of the average will actually be larger than the variance of just one. And if I keep on adding more information, my variance will keep on increasing, so my inaccuracy will keep on increasing. Right? So it's important that when you're weighing your oranges here, you must mix all the oranges well before you do this exercise. Yeah, you can't just take something from the top. Otherwise, just adding more information will actually increase the variance of the estimates. Yeah? Sure? Okay. Now, so we have showed the important part that x bar is normally distributed with mu and sigma square upon n. Approximate. With the approximation getting better and better as the sample size gets larger and larger and larger. All it follows yeah. So I know, for example, that probability yeah. If I wanted a 0.9p, then this will be minus 1.6 plus 1.6 something of it. And I can always find those numbers. Right. Okay. Now, let me go back to that example of elephants and all that. Right? So suppose that the mean weights of healthy elephants, the mean weight of a healthy elephant is say 5 tons. Yeah? Okay? And suppose the elephant weights have a standard variance of 4. Right? So the mean weight of a healthy elephant is 5 tons. And not all healthy elephants are exactly 5 tons. Some healthy elephants are fat, some healthy elephants are lean. So there is a variability in the healthy elephants population. So this is their variance is 4. Right? Okay. Now, I have picked up, I have got some elephants. So I have got 4 elephants. I am keeping n deliberately small because there is a certain illustration. Right? So 7. The first elephant weighed 7 tons. The second elephant weighed 3 tons. Right? The third elephant that I caught weighed 8 tons. Okay. And say the last elephant was a big hulk which I caught for, which was weighed for 12 tons. Right? A really fat elephant is what I caught. So there are 4 elephants I've caught. And I am asking the question, could these elephants have come from the population of healthy elephants? Could these elephants have come from the population of healthy elephants? So, I have got these 4 elephants. So, I am going to now, my evidence is a collection of these 4 data points. This is the information I have. I aggregate that information into a single point. What do I do? 7 plus 3 plus 8 plus 12 upon 4. That is, I put 1 by 4 into 7 plus 1 by 4 into 3 plus 1 by 4 into 8. Yeah? How much is that number?
30 by 4.
30 by 4
30 by 4.
is 7.5. Right. Now, if I assume, so suppose let me start by assuming that these elephants come from a healthy population. If I assume that, then this is the sample that I got. These are all random elephants, so I didn't catch a single herd. I am assuming that I got elephants from all parts of the forest. They are all unrelated elephants and all that kind of thing. Right? Okay? Sure? So if I catch X bar, I know that X bar must be normally distributed with mean 5 and variance 4 upon 4. Because 4 is my sample size. So if my hypothesis is indeed true, that these elephants have come from a healthy population, then I must have X bar normally distributed with mean 5 and variance 1, or X bar minus 5 upon 1 must lie between minus 9.56 plus 1.9 minus 1.96 plus 1.96 95% of the times. Right? Okay. Now, what is X bar? 2.5 doesn't lie in that boundary. Right? 2.5 doesn't lie in that boundary. So how do I interpret it? I interpret it as follows. There are 2 ways of interpreting it. One is to say that, look here, only 95% of the healthy elephants weigh, are such that this X bar minus mu upon sigma by root 10 will lie between minus 1.96 plus 1.96. For 5% of the elephants, it can lie out of those boundaries, and it is those 5% of the elephants that I am seeing. So, I say that there is really no conclusive evidence against these elephants being not from this population. There is a 5% chance. Somebody might argue, yes, there is a 5% chance, but 5% chance is too low. In the sense, if we are really concerned about elephants, and elephants are really precious, and we want to desperately identify unhealthy elephants, and it's okay even if we catch some healthy elephants and think of them as unhealthy elephants, because elephants are very rare, right? Okay, so if that's the case, let's take this 5% risk. Let's allow for this 5% chance of being wrong, and let's say that these elephants are not from a healthy population. In which case, I will be saying that my evidence is not consistent with my null hypothesis with a 5% chance of going wrong. That is called type 1 error. Right. In the real world, what you really do is, so you find this Z. This is called the Z value. Suppose you find it here. Suppose you find that the chance that the value on the distribution to the area to the left of the Z and the right of the Z is 36%. So 36% is the chance. If so, 36% is the mistake that you will make if you classify this set of elephants as unhealthy elephants. So once you know this, it helps you to take a call. It says, suppose I take them as unhealthy elephants. Then I am not going to miss out on any unhealthy elephants, but 36% of healthy elephants I will classify as unhealthy elephants. Right? So there will be some large number of healthy elephants who are with me who are being treated. If you think that the cost of treating healthy elephants is very large, but the benefits of treating unhealthy elephants are not so big, in which case you might not want to take that call. But if elephants are very, very scarce, that these are some animals like the great Indian bustard, for example, they're very few. You would say perfectly fine if I get 10 healthy bustards to be treated, but I don't want to miss out on a single unhealthy bustard because it's an infectious disease and this will spread and all the healthy bustards will die. Then if you're careful about that, then you would say you will be willing to take even these large type 1 risks. Right, so you have to take a call depending upon the business position. Right? Previously we used to do it 5%, 2%, 3% kind of a thing because that time we did not have these quick desktop computers which will give you these probabilities quickly. That time somebody had to write down the values. Somebody had to tabulate them and like that. Now we don't have to. So it becomes the error that you are willing to make, the chance that you are willing to make is called the p-value. So what you have to look at is the p-value. The larger the p-value, larger is the probability of misclassifying healthy elephants as unhealthy elephants. What p-value you accept, settle for, there is no hard and fast rule. It all depends upon what is the implications of misclassifying. Yeah? And the decision that you are going to take. Sure. So that's also, therefore, I never teach things in terms of rejecting a null hypothesis if it's 5% or more. It doesn't work like that because it's ultimately a decision that you have to take or to do something in mind. And all that this helps you is what are the chances of miscalculation, what are the chances of a wrong decision. You need to be able to evaluate your own, your own cost benefit analysis on the basis of that. But that's the kind of a call that you have to take here.
Question. So your X bar is 7.5, which is higher than 5. But what if my X bar was 3.5? Would have that been correct or?
So if my X bar was 3.5, then what I get? My Z will be 1.5, right?
So it will be on the left side of.
Yeah, it will be on the left side. But then you would say that the chance that Z lies between minus 1.96 plus 1.96 is 95% of times. So finding an X bar which is 3.5 is not very surprising given my null hypothesis, and therefore it is not, I can easily find populations of healthy elephants whose average weight is 3.5, who weigh less than the normal. By pure chance I can find a group of people who weigh less than the normal. Right, but what I found is not so large to say that these people are abnormal. Right, in fact this is a very similar idea gets used when you identify kids as malnourished. What they typically do is, they will look at what are called height to weight ratios, etc. Right? Weight for age ratios. So basically you will do a survey of kids, you will find what their weight for age ratios are, height for weight ratios are. And then what you will do is, there is a healthy population of healthy kids, which is given to you by the World Health Organization. So what should be the distribution for weight for age for healthy kids around the world? Right? From a WHO population. And then you will say that my child is unhealthy if it lies in a way, if the weight for age for that child lies in the lower tail of that distribution. Yeah? Lower, so it's, for example, the child's weight for age is so small that the chance that a healthy child has such a low weight for age is about less than 0.5%. Then you would say the very high chance that this child is malnourished. Right? That's how you actually identify malnourished children. Right? And there are lots of debates about whether you should use populations of healthy children because these are healthy European children, and should Indian children be compared to healthy. So there are all types of all those kinds of debates everywhere. But that's the general kind of a methodology to do this. Right? So this idea is really used in a very large number of situations. Right? So obviously you can't have a hard and fast rule of 5% when you're looking at deciding whether children are malnourished and whether, say, on something which is not so critically important. Right? So therefore it all really depends upon what kind of issues are at stake. Right? So we'll break for a cup of tea and then we'll come back. Thank you.